Good morning, everyone. I'm sorry that we are starting just about 8 minutes later than planned. There were a few technical errors in the internet connection on my side. I hope this will not prevent us from continuing. Um, my name is John Ernie. I'll be presenting today's webinar on polymorphs and pseudo-polymorphism by means of differential scanning calorimetry. Just as an introduction, I wanted to let everyone know that you can use your GoToWebinar tool panel to ask questions. I would very much look forward to receiving questions from you. The beginning of this presentation, the first 45 minutes will be presentation component, and then we'll follow that with a question and answer session. With that being said, and because I know we are beginning just a few minutes late, I want to go ahead and just get right into this. So here at NETCH, the NETCH family comprises three different groups of three different companies. The analyzing and testing portion is the group that I work for. This includes thermal analysis instrumentation and determination of thermophysical properties. So we're definitely an old company. We've been around since the 1870s. We're a mid-sized company. And apart from the analyzing and testing groups, especially for pharmaceuticals, it's good to know that we also are on the process side of things with grinding and dispersing, as well as pumps and systems for pharmaceutical grade applications. Very small bit about your host today. My name is, again, John Ernie. I am a regional technical manager and regional technical sales associate for NETCH, covering here in the US, Texas, Louisiana, Oklahoma, as well as Mexico. My background is in chemistry. I've worked in the polymers, oil and gas, and pharmaceuticals industry, primarily from an analytical chemistry standpoint. I've been with NETCH since 2017 in my current role here, based in Houston, Texas, and covering pharma for the US, but most accounts here within my local region. So let's get right into it. What we're doing is we're looking at polymorphs using differential scanning calorimetry. If you're not familiar with the technique of DSC, many of the, we're not going to go into fundamentals because we covered that in the previous component of this series in part 1. We are now in part 2. But even if you're unfamiliar with DSC, we'll be talking about the concepts throughout, because that's primarily the data that we'll be investigating. So what we have here is what you would generally expect in a DSC trace of a pure pharmaceutical compound. On the y-axis, of course, we have what is called the heat flow. This is either endothermic or exothermic events associated with the heating or cooling of a compound. What we have here is ribavirin. This is an antiviral compound that we've got here. We've got a sample mass of 1.02 milligrams. We're heating our sample at 10 degrees Kelvin or 10 degrees centigrade per minute in aluminum crucibles, nitrogen atmosphere. And what we can see in the range of 140 degrees C up through 180 degrees C is we have a very clearly defined onset of our melting. So as we're heating the material, we have no endothermic or exothermic events until we reach the melting of this crystalline compound. So we have the so-called onset temperature, which is an extrapolation of the baseline and the tangent here with the slope of this melting peak. We also have the point of maximum heat flow. So you can see the onset and the peak temperature. And in your pharmacopoeia, you should have both of these very well defined, as well as one thing we can look at is the area under the curve here. So this is, again, a very well defined melting of a crystalline compound, very straightforward. But let's look into a little bit more, more complex examples. This particular compound can exist as two different polymorphic forms, A and B. And as I mentioned, we're looking at polymorphs using DSC. So we'll be defining polymorphs and looking more into DSC throughout the course of this webinar. So how do we get these different forms of this same material? Form A, we're looking at a material that's crystallized out of aqueous ethanol, so ethanol with a water component, and it has a given melting range from 166 to 168 degrees Celsius. But then there's also a Form B crystallized from pure ethanol, and that has a melting range that is a bit higher, 174 to 176 degrees Celsius. So for this particular substance, it has the same stoichiometry, the same chemical formula, but the physical structure of the substance is different. So for certain substances, we have not only one melting point, but we can have multiple melting points. The example that we showed before is, of course, Form A, based on the melting point, that onset and the peak temperature that we saw. But one of the ways that we can distinguish between polymorphs, as we can see, if I have A and B, and I can find out what their melting is of my real sample, this allows me to distinguish between the two different polymorphic forms. And this is a very basic, very first form of using DSC for polymorph studies. So let's dig in just a little bit deeper into what is polymorphism. So this is the exact same material, and we're looking at solid materials existing in different crystal structures. So again, same stoichiometry, same chemical composition. You might be a little bit more familiar if this is a difficult concept to grasp, or if this is new to you. Chemical elements also exhibit this, not just compounds, not just heteromolecules, but also just individual elements. So for example, carbon can exist as graphite, as diamond, or as these so-called fullerenes. We have the same carbon molecules, they're simply arranged differently, either in a stacked and layered form, either small groups with graphite or large sheets with graphene. We can have a tetrahedral arrangement of these same molecules with diamond, or of course then these buckyballs or fullerenes, Buckminster fullerenes as they're sometimes known, in a completely different orientation, but still the same element. So that's polymorphism, so the same material existing in different crystal structures. We also have pseudo-polymorphism, and this is going to be a special case of polymorphism in which the different crystal types are simply the result of water addition, so hydration or solvation. So crystal structures that have incorporated within them some of the local solvent molecules, be that water or be that another solvent molecule. So no overview is complete without a very brief historical view. Going back all the way into the end of the 18th century, so 1798, Martin Klaproth looked and saw that calcite and aragonite are just simply two different forms of calcium carbonate. So the exact same chemical structure, this calcium carbonate, exists in an orthorhombic or in a rhombohedral geometry. And based on thermodynamics and kinetics, so basically looking at what temperatures is the material existing at, and at what time, how long has it been at that given temperature. One form can then be converted into the other form within a few days. We can also see that there's then even a third polymorph with a different crystal structure, which is even, of course, less stable then. And then the actual term polymorphism, meaning multiple shapes, coming from that Greek base, was defined already early in the 1820s. So this is nothing new, but we do have new means of studying these different structures. And why is it important? And this is really the question ultimately when we're going to be using analytical instrumentation or spending our time investigating substances. What's the real critical reason for us to do this? So having the same material, the same substance with different organization, different polymorphic forms, this can adjust the melting point, the sublimation temperature, as you can see here, heat capacity, volume, viscosity. So those are all physical properties, but from a pharmaceuticals perspective, the real impact is that the processability of drug substances and the shelf life. So we're looking at stability, how hygroscopic the material is, that is, how much water does this absorb, and then of course that relates again back to shelf life, and that can relate to bioavailability. And we also need to look at dissolution. So the same crystal structure, same material with different crystal structures can dissolve differently. They can be available for activity within the body differently, and they can have different shelf lives, even though they have the same chemical structure. So I mentioned we would go into DSC, and we will be looking a little bit more into the DSC. I apologize here. I actually have some German slides content. I know this is the English language version, but we'll work through it. As is the convention, we can display the DSC traces either with endotherms, so heat flow into the sample up or downwards. It is the standard European convention to display endotherms in an upward fashion, so melting peaks will be displayed in an upward fashion. I know that here in the US, where I'm broadcasting from, many providers of thermal analytical instrumentation have the opposite convention. All software packages can allow you to reverse this. So really we get the exact same information. It's just a question of, is endo up or endo down? So we also have this nicely color coordinated, red and blue, red intuitively for heating, blue more intuitively for cooling. And so what we have here is indium. This is one of the most commonly known calibration standards used for looking at DSC. Now, what makes it a calibration standard? This is just a pure metal, and it has a very clearly defined onset temperature, literature 156.7. We can see here the onset temperature of melting, again, as the tangent of the intersection of the tangents of the baseline and this rise in the melting. This onset temperature of 156.6, so very close to literature here. The other important point is the area. Sorry, that's again German here, but the area under the curve in joules per gram. So how much heat energy is required, how much energy is required to go from solid to a completely liquid state. So that's the area under the curve here. And you can see as we heat the material up, we get a melting that is then complete. We can then take the material and go from these high temperatures down to low temperatures, and we go through then the crystallization. We can then see very closely matched the area under the curve. But what you might also notice then is that we have an offset. There's going to be a different process that describes or that dictates crystallization from melting. Melting is a thermodynamic event, whereas the crystallization is a kinetic event. If these terms are a little unfamiliar to you, the thermodynamic event is going to take place at the given temperatures, relatively independent of time scaling. However, when we go from the liquid to a solid, we're going through a crystallization. What's going to happen is that crystallization is going to be time dependent. It takes time for those liquid molecules to orient themselves in relation to each other and form that crystal lattice. So that's why we're seeing this offset known as hysteresis between the onset of melting and then the onset of cooling. But really what's important for a calibration standard of any type is that you have repeatability. Repeatability, reproducibility, precision. And so what we have is simply 7 runs of the same material, heated, cooled, overlaid, and very nicely, consistently showing us the exact same properties. This is one of the ways that we're going to not only calibrate our system, but we're also going to use this as a conceptual tool to understand what's going on in our system. With a simple metal, as we're heating and cooling, we're getting complete reproducibility. Not necessarily so with our polymorphic materials. This is a simple metal. When we're looking at more complex structures and we get into polymorphism, it's not always so straightforward. And it doesn't have to be a complex structure for us to get something that's not 100% straightforward. If we take ice, very pure, deionized, filtered water, we make sure that we use a very clean crucible. This is an aluminum crucible that's been solvent cleaned, baked. We make sure that the water is extremely pure. And as we go from solid to liquid, of course, everyone understands the melting of ice, very nice and easy conceptual process. We have that onset right near 0 degrees Celsius, and then it's completed. But then what we see under cooling is we get the material all the way down here to negative 15 degrees Celsius, and there's still no crystallization that's taking place. Again, that melting is a thermodynamic process. The cooling is a kinetic process, and this is something that you might have seen before. This is known as supercooling. We reach here some critical point where there's the onset of crystallization, after which point we have a small seed crystal, and then that provides a lattice, after which the rest of the water molecules, which are already well below their actual freezing point, then arrange themselves around that, and we get a very rapid cooling. So looking at polymorphs, so we've looked at some basic calibration materials, some very common materials, indium and water. When we're talking about polymorphs, it would be very nice if there were a standardized way of describing these different forms of the same substance. And in the beginning, what was attempted was to use Greek letters alpha, beta, Roman numerals 1, 2, Latin uppercase A, B, to characterize these forms in a systematic way. And the idea was the modification or the form of the material with the highest melting point is generally named form 1, alpha, or A. Unfortunately, this is not always the case. Sometimes a more stable form is found later, and then things are changed. So while in general, you can see form 1 or A or alpha as the highest melting point temperature or highest melting point form, this is, of course, this is not always the case. So take this with a grain of salt. You'll also see things at metastable modifications, so things that are not permanently stable, sometimes marked with this prime. And so we need to let's formulate some concepts around polymorphism before we actually look at the DSC data. What I'm going to do is go through a few more conceptual ideas before we go through and look at about 4 different examples of polymorphism studies and what we can pull out of it from the DSC data. So let's take this empirical observation. So we take a material, and cooling the material from the melt, what we end up finding is that the thermodynamically least stable modification crystallizes first, and then you get this rearrangement, this recrystallization, and you get a step-by-step formation of more stable forms. So these are discrete steps. This isn't the material partially crystallizing and then partially crystallizing. Depending on the kinetics, depending on the rate of cooling, what we can arrive at is a discrete series of these metastable states, and then we end up in this more stable phase, which again will have that higher melting point. Along with these crystalline forms, again, depending on the cooling, because it's a kinetic process, a time-based process, we can also end up with an amorphous phase. So phases, amorphic, crystalline. Let's look at a little brief overview of different states of material, different phase transitions, so that we're all on the same page. This is coming from a text. It's a text from the 1980s, very commonly used in Germany, also translated into other languages. But what we have here on the left-hand side, we've got entropy and enthalpy of our materials increasing as we go up. We have density of our material decreasing then as we go down. So if we look at a crystalline form of a material, let's say the alpha form, the most stable form, this is something we're very familiar with. We know this terminology. We have melting and crystallization as we go from that crystal form to a liquid form. We could also have a less stable form, and we could have that solid transition. So we can have that crystal transition. We can have a solid transition from crystal form A to crystal form B. Of course, we also know the terminology here, basic physical chemistry, going from liquid to a gaseous state. We've got evaporation and condensation. But these don't describe the full range of possibilities. We have sublimation and then desublimation, going from gaseous directly to solid forms. You'll see this with things like liquid nitrogen and solid and dry ice. But then we have the so-called liquid crystals, which are a little bit more liquid but retain some crystalline structure to them. We also have glassy state materials, which are more solid but which retain some degree of that liquid form. So there is quite a large range of different material phases, and the important thing is that based on their thermodynamic stability and the kinetics, we can use the differential scanning calorimeter to pull out what phase of material do I have, or what phases of material do I have. So let's get into some of the examples. This is what I know a lot of you are waiting for, and this is, to me, the really exciting part. Is we've looked at some of the background. Let's look and see the data. What can we actually pull out from some concrete examples? You might recognize sorbitol. This is a C6 sugar. This is something that you'll find in a lot of different food products, also a sweetener for various different pharmaceuticals. And what I'll show at the bottom are just experimental conditions. Often with these materials, we'll have somewhere between 1 and 5 milligrams. Most of the USP, the US Pharmacopoeia, as well as other standards, recommend for doing basic studies, we're looking at about 10 Kelvin per minute heating and cooling. But if we want to do particular studies, we can of course change this. We can go slower, we can go faster, depending on the particular goal of our experiment and whether or not we are using a particular standard or we're doing our own individual R&D. We might see aluminum crucibles either pierced or pierced and open to the environment, or closed and sealed. Since we're showing nitrogen atmosphere, of course, this would then be a not sealed component, not sealed experiment. So as we're heating our material, what we see is a single crystalline phase. We have the onset here, and then we have one simple melting. But then after we cool, let's say we cool this material, we take it from solid to liquid. We then cool the material, and we cool it at 10 degrees Kelvin per minute. Then we heat it up one more time. Now this looks completely different. What's going on? Well, I mentioned that cooling, that crystallization is a kinetic event, or a series of kinetic events. It's not simply that we reach a certain temperature and the material crystallizes. It's a time-based process. So if we're cooling this material at 10 degrees Kelvin, and then we immediately start heating the material, we go through this step change, we go through a glass transition, and then we don't see a crystallization. What this means, with a little bit of knowledge of the materials and DSC, is that we were actually in an amorphous state. Glass transitions are associated with the materials with an amorphous phase. However, if we then go through and store this material one day at room temperature, we allow the kinetics of crystallization to occur. We then see a different story. We heat up the material again, and then we have not this melting, at this onset of 95 degrees, but then we have an onset melting of, down in the upper 70s. We have an onset of melting down here around 50 or 45. So we have different phases of this material simply after being stored for a number of days. So depending on the shelf life that we're interested in, we need to look at storage conditions. We need to look and see, well, if we want to maintain an amorphous phase, do we store it at room temperature, or do we need to store it at a lower temperature? And what are the actual physical properties of these? What is my goal? What form do I actually want to have? So this is going to dictate our storage conditions, but this is how we can use DSC as a very simple tool to evaluate what form have I received my material in, versus how do I want to then process that material and send it out. So this leads us into a few more definitions. We don't only have one simple type of polymorph. There are multiple different types of polymorphs. There are those that are reversible, that go through reversible phase transitions. There are also those which go through irreversible phase transitions. So we have the so-called N-antiotropic transitions. These are reversible. So as we go from a low temperature state to a high temperature modification, we have one form that is under all conditions more stable at higher temperatures, and one that is more stable at lower temperatures. So if we look at a plot of the Gibbs free energy of the two different phases, or the two different polymorphs, below a transition temperature, this TT, we can see the pink material has a lower Gibbs free energy, i.e. will be more stable below this transition temperature, whereas this alpha, the alpha form above the transition temperature, has the lower Gibbs free energy, and thus will be more stable at this higher temperature range. So depending on whether we want to, let's say that we want to have primarily polymorph A, what I can do is allow the kinetics of recrystallization to happen above the transition temperature, and this higher temperature, at this higher temperature, I'll end up with more of this polymorph A. If I'm interested in polymorph B, then what I can do is maintain my material down at this lower temperature, to ensure that I have the more stable material down here. And we can formulate you know, reversible and irreversible polymorphic transitions and look at these different enantiotropic forms. There's a few different rules that came out of the 1970s. These were published in Microchemica Acta by Professor Berger. And these are so-called the Berger rules and the Ramberger rules. And these relate to solid-solid transformations. Again, going between different solid states of these materials, going between different polymorphic forms. And so what do these rules say? How do they guide us? The only reason we want to have rules is to help us think through and understand what's going on. So the transition enthalpy of these two enantiotropic forms, that is reversible forms. So above the transition point, we're going to have an endothermal effect going, and below the transition temperature, we actually have an exothermic event. Endothermic and exothermic, that's when we're looking back to our DSC trace and seeing, do I have heat flow into my material, endotherm, or heat flow out of my material, exothermic? So this is going to be a nice guide for us looking at a DSC trace and knowing whether I'm getting heat flow into or out of, am I above or below that transition temperature? So that's the heat of transition rule. If we're looking at the heat of fusion rule, so this is, instead of looking at transition heats, what we're doing is looking at differences in the melting heat, so the melting enthalpy. So if I have form A versus form B, am I going to have a higher heat of fusion or higher heat of melting of form A or form B? How am I going to know? Well, the higher melting form, so this is the material that melts at a higher temperature, it's going to have a lower melting enthalpy. So that's the area under the curve for this particular enantiomorphic pair. So it's a really nice simple rule. The higher melting form has a lower melting enthalpy. If the higher melting form, though, also has a higher melting enthalpy, the relationship is monotropic. What does that mean? It means instead of enantiotropic, having this reversible transition, if the higher melting form also has the higher melting enthalpy, we have a situation which is monotropic. And we'll talk about monotropic forms here in just a little bit. So you can imagine we have a lot of different ways that DSC traces could look and we're looking here at some data that's very, very nice. This was again published in the Journal of Thermal Analytical Calorimetry. This was from a Swiss researcher working with pharmaceuticals, and this shows heating curves from a DSC and a lot of different potential ways that the curves could look, and we'll break them down one at a time. So what do we have? So in this case, we have two different forms. We have a pharmaceutical compound which has two different forms, simply A and B. And so what's going on? As we're heating our material, we have, in this first case, an endotherm, a small endotherm, and then another larger endotherm. So what we have here is stable form A transforms into form B. So this is an endothermic effect. And then that form B melts. What about in condition 2, the next one down? Stable form A simply melts, and then the transformation into form B is hindered kinetically. What does that mean, that it's kinetically hindered? It means that we're going through this process too quickly. Where we might transition into B, this heating is happening too quickly, and this process would take time. So kinetically hindered means the process is happening too quickly, and the thermodynamic process takes over. So what about example 3? So we have stable form A that's melting. Form B, so stable form A melts here. Form B is growing from that melt. So we're getting a recrystallization into form B. That recrystallization is providing us with a more thermodynamically stable compound. So that's giving off heat. That's why we have an exotherm. And then form B is melting. If we look down to this fourth example, what we could have is a metastable form B that's transforming into form A. So metastable form B has a higher Gibbs free energy than that stable form A. So we're giving off heat to transition from B to A. But then A melts. A transforms into B, and then B melts. So we can see a lot of different transitions. Metastable B transforming to A transforming to B melting. And then of course at the very end we have the most simple version, which is metastable form B, melts. We have no transition to A, no transition back to form B. So let's go ahead and look at this. Let's go back to some DSC data. If I want to look at this N-antiotropic transition, I have two different phases of cesium chloride. So I have one phase that is a face-centered cubic and one that is a body-centered cubic. So this would be a structure that is more like sodium chloride, whether we have a cubic, like a straight square, versus something that looks a little bit more orthorhombic. So cesium chloride goes through these reversible phase transitions, just like the indium, or in a similar fashion to the indium. Whereas the indium melts and recrystallizes into a single form, the cesium chloride goes between two solid forms. So on the first heating, we've got the first heating in red, and I have a nice onset temperature that occurs here. And then cooling, I then go back into the body-centered polymorphic phase, polymorphic structure. And this is then something that occurs repeatably. I then have a second heating, and once again, I have this nice stable onset. We can see a slight difference. We can see a slight difference here. And you might say, well, this looks very unrepeatable. What is going on? Why do I have this difference between this first and second heating? As I'm going through this first and second heating, my material is physically changing and physically adapting to the DSC pan as I'm heating it. So if I have a second, a third, fourth, fifth heating, I'm going to see a nice overlap between those subsequent heatings and coolings. Whereas on that first heating, maybe just the way that I prepared the sample means that it's not conformed to the DSC pan in an ideal fashion, or it simply rearranged itself, via gravity and this transition. So this is not a solid liquid transition. This is simply a solid solid transition, and then a solid solid transition back to the previous phase. So again, N-antiotropic, this is completely reversible, and it's happening. We're having a thermodynamic process. This particular one, and then I'm sorry, that was me misspeaking. So we have both of these are actually kinetically driven processes. We talked about N-antiotropic, and those were situations where we had two compounds that crossed at some transition point. If we look at monotropic polymorphic transitions, these ones are irreversible. And so what this means is that only one of these solid state transformations is going to be observed. So if we begin with the less stable form, once we convert it into a more stable form, that's the only transition that we're going to see. So if you have these polymorphs alpha and beta of a particular material, so below a given transition temperature, the pink form is more stable, but above a given transition temperature, the form B is formed, and then we never actually go back. We never actually convert back into the modification B to this beta form. So once we've processed the material into the alpha form, it stays in that alpha form. As opposed to the N-antiotropic situation where we have multiple transitions where we can go back and forth between A and B in these N-antiomeric situations. With these monotropic transitions, it's a little simpler. So instead of 5 or 6 examples, we now just have 3, and we will start with the most simple example, which is this number 2. We've got stable form A, simply melting. This is the example that we saw at the very beginning when we were looking at something like Sorbitol or the ribavirin. We have one stable form that is melting, and we have that crystalline structure melting, and we go from solid to liquid. What we could, however, have is that metastable form B that is less stable at all temperatures than A, transitioning, and we see this exotherm. So we go from a less stable to a more stable form. We will see that exothermic event. So we're transitioning to form A, and then form A melts in a similar fashion to form A melting here in number 2. The last example that we can see here is the metastable form B doesn't convert to A, but for a particular compound, what might happen is the metastable form melts, and through the melt, we then have the freedom within that molten structure that the stable form A can form, and then form A melts. And so you might wonder, so I have an endotherm, I have an exotherm. Why is there this overlap of these endothermal and exothermic events? So B melting is going to absorb energy. Any solid to liquid transition that we're going to be looking at here is going to involve heat put into the system. But then the rearrangement of the molecules into a stable form A, into a more thermodynamically stable arrangement, gives off heat. So I go from adding heat to the system that sample then giving off heat, and then heat being put into the system through that melt. So along with DSC, there are a number of different ways that we can look at polymorphs. X-ray diffraction is a really popular technique. You can look at powders or single crystal forms if you're able to crystallize your material down to a single crystal. We can look at infrared spectroscopy or Raman spectroscopy. And in all of these situations, we have non-destructive techniques in which we are using a form of a portion of the electromagnetic spectrum, and then specialized detectors to directly look at either the crystal lattice or vibrational effects that are going on. We can also use thermal microscopy, so using high-powered microscopes. And just like we can do the same thing with thermal XRD, to take our material through different phase transitions or different solid-solid transitions, and then look at the material structure directly. So if we have these other techniques, why use DSC? Well, DSC is something which we already have in the lab for a lot of other purposes, for looking at purity studies, looking at reaction kinetics, and it's also something that's very, very easy to handle. Sample prep is very easy, and the experiments can be carried out very, very quickly. So these different complementary techniques can be used, and you might find them all within your lab, but DSC can provide us, as we've seen, a lot of different information. So those were us building up all of this information, all of this knowledge about our systems. Let's go through and look at some examples. Like I said, we've got 3 examples here to close out the webinar portion, and then we can then go through and look at questions at a Q&A session at the very end. So what we have here as one example is the paracetamol. We've got 3 different literature values. So we've got 3 different forms, form 1, 2, and 3. As we can see, we've got form 1. This is following the nomenclature that we would ideally like to see for most of our compounds, where the form 1 has the highest melting temperature, and then going down to form 2, lower melting temperature, and even lower. In some of these situations, we don't have a set heat of fusion that can be found. If we look up literature values, often what we'll see is kilojoules per mole. What we do then, if we want to look at this in terms of the DSC and the way that we've prepped our sample, we can see the amount of joules per gram, so the area under the curve of melting for these two different forms. So let's take some paracetamol. Let's heat it up. So again, using a very small amount of sample, 2 milligrams, heating at a relatively fast heating rate, 10 Kelvin per minute. I say fast because one of the things that I'm used to doing is looking at purity studies, and in purity studies we're often using 0.7 to 1 degree Kelvin per minute. So doing polymorph studies we can do much faster. So we're using aluminum crucibles, again with a pierced lid in this case, so they're open to the environment. And what do we see? We see an onset temperature of 169.2 for the onset. Well, if we go back to our table, this shows us a very nice, very clear indication that we have form 1. I don't see any effects happening at 156 degrees Celsius, so I see no effects here in this region. So what this tells me very clearly from the DSC is that I have this stable form 1. So let's heat the material. I've got that first heating. I then cool the material down, and then I heat the material a second time. This is a situation where I now have an entirely different event. So if we think back to the enantiotropic examples, we had 5 different examples. We could have stable form A, metastable form B, form B. So what we have here is we have one form. We have an exothermic event right here. We have an exothermic event, which means a recrystallization or a structural transformation. We're going from a less stable to a more stable state. We're always going to know that's happening when we have this exothermic event. And then we have another melting, this time at 156.9 degrees Celsius. This then very, very nicely overlays with that form 2. So based on the thermal processing, on the thermal history of the material, we can very clearly see as received, we have the form 1. After processing it in the fashion that we have, heating it up at 10K per minute, cooling it down, and reheating it, we can then arrive at this B form, at this form 2 rather. Let's take another example. We have this second compound that we're going to be looking at, which is going to be a little bit harder to pronounce if you want to look at the actual structure here, this carbamazepine. This one it's not only a little bit harder to pronounce, but also has a lot more different forms. And you can see this mixture. We've got form 1 or alpha, we've got form A2, B2, 3, or B4. So a lot of different structures. We've got 5 different structures that are reported in literature with a range of different melting temperatures. And we can find literature values also for the heat of fusion, or the melting enthalpy for 3 of these different forms. So even on the very first heating of this material as received, we can see that there's one endothermic event with a peak temperature of 160 degrees, and then we can see a second endothermic event with this onset of about 190 degrees Celsius. Again, small sample, 10K per minute heating rate, pierced lid. This is going to be critical. One thing that we can look at, so we've got the first heating, we have a nice stable baseline all the way through until we get to these events. On a second heating, after cooling with a very fast cooling rate of 40K per minute, what we can see here in the very beginning is we have a step change. Well, we have a step change in the specific heat of the material. As you might remember, this is a glass transition. What types of materials have glass transitions? Amorphous materials. So what this indicates is that by cooling the material very quickly, we have kinetically hindered formation of crystal lattice, at least in a portion of the material. And so we have an amorphous structure that goes through this glass transition. We then have this exothermal event. I'm a little bit off this morning. We have this exothermal event, which, if you recall, and we'll say it again, any of these exothermal events are us finding a more thermodynamically stable form. We're going from a less stable form to a more stable form, or from an amorphous to a crystalline, a more highly ordered structure. I then have a melting with an onset of 186.4 degrees. I can go back and look at my table and compare and see, all right, which form do I have here in this state? If I look at the same material, and instead of cooling with a very fast cooling rate of 40 degrees Kelvin per minute, I heat that same material and I cool at 10 degrees Kelvin per minute, I have a very different situation. So first heating, this is what we saw in the last one. Now I cool down. On my second heating, I no longer have that glass transition. I no longer have an exothermic recrystallization. I simply have that same melting that I saw in the last curve. So what's going on? It's kinetics. I mentioned that kinetic hindrance can play a large part in the way that we have different polymorphs, in which forms exist. When we cooled really quickly, we froze the material in its amorphous state. When we cooled more slowly, we allowed the material time to find a more thermodynamically stable form during the cooling process. How is this relevant for you as pharmaceuticals, scientists or engineers? This is going to dictate the way that we process our material. Is going to then lead to which forms are present in our material when we're finished with it. Also, looking at shelf life, looking at how do we store these materials. If I need form A or form B for bioavailability or for processing, how do I need to store these materials so that I have the form that is desired? Let's go ahead and look at another very, very common drug. This is a sulfathiazole. This one has 4 forms reported in literature, 4 different melting temperatures, different heats of fusion. One thing that I can say is that all of these webinars in this series will then be posted on our website. You can go back through and download these, relook through this material at your leisure. And so I'm not going to be coming back to these tables. I'm just going to keep on plowing forward through these. So the sulfathiazole as received, as we're looking at this material, undergoes two of these endothermic events. Remember, if we look back to the Berger rules, if we're looking at these endothermic events, we can look back and see that we have a more stable going through into a metastable form, and then we're actually getting a complete melting right here. We can also see a slight transition. We can see some effect that's happening right here, right before this onset. And this is something that we need to look at. This could either be my material conforming to the pan, but if this is a repeatable event, this is something that I look and say, this wasn't just my sample preparation. What we have here is we might actually have multiple different forms in the material as received. So I could have a mixture of forms 1, 2, 3, and 4. In this case, I only have 3 forms. I might have forms 1, 2, 3, 1, 3, and 4, however the case might be. But as we're heating, and depending on the heating rate, we could also see transitions from more stable forms, or sorry, from less stable forms to more stable forms as we reach this final melting. One last example we'll go through and look at, and this is, we talked about polymorphism. The last thing I want to look at is what we talked about in pseudo-polymorphism. So this is something that we're going to look at. This is estradiol hemihydrate, and you see this second portion of the name, this hemihydrate. Hemihydrate meaning that we have in the crystal structure for every molecule of this pharmaceutical compound, we have half a molecule of water. Of course, we don't have half molecules of water. What this means that is in bulk, we have a ratio of 2 to 1 pharmaceutical compound to water in the crystal structure. So 2 simple forms, form 1, form 2. Let's take this material and let's heat it up as we've done with all of our other materials. And this is something that we haven't seen before in the other examples. Now, instead of nice, very clearly defined peaks with nice peak shapes, now, along with this melting peak, we also see this large, broad endotherm ranging from about 80 degrees Celsius all the way up to about 150 degrees Celsius. This is where it's going to be critical for us to look at the way that we process our samples. So we've got a couple different samples. We ran the samples in a couple different conditions. So we've got anywhere from 1 to 5 milligrams, same heating rate. We ran these in aluminum and alumina, so aluminum oxide, so metal and ceramic crucibles under nitrogen atmospheres. I wanted to see, all right, what exactly is going on here? Sometimes we need to look at these samples from a slightly different perspective. When you looked at the material, it's a hemihydrate. Hydrate means there's water. Water, in a lot of cases, is going to be available for evaporation. It's not going to stay with the material throughout the whole process. So as we heat up our material, let's look at a thermogravimetric curve. So if I look at the mass of the sample as a function of temperature, as I have this endotherm, we've been looking at these solid-solid transitions so long, you might be in the mode to think this is a solid-solid transition, when in fact, what we have is a solid to gas transition. So this might be solid going to liquid, liquid converting to gas. So that hemihydrate, that water that's bound in the crystal lattice, is being released from the crystal lattice and evaporating. You can see very clearly we have a very nice overlap between the endotherm on my DSC trace and the mass loss that we're seeing on the same material run in this alumina crucible on the TGA. So for the DSC, I ran a slightly smaller amount on the TGA just to make sure I got a little bit nicer signal. I ran 5 milligrams of this same heating rate. That way I could overlay very nicely. So what we're having is the loss of water followed by the melting of this crystalline structure. This is where the way that we run our material is very, very critical. So if I run my material in an aluminum crucible with a pierced lid that is open to the environment, the water can evaporate. I have what we just saw. We have the evaporation followed by crystallization. If I run this in a closed aluminum crucible, in which case the water has nowhere to go, that it's retained there within the crystal lattice, then I have a more broad melting peak influenced by the water that's present. So I no longer have this nicely pure estradiol. I have the estradiol hemihydrate, which, as we saw in the last webinar within this series, we saw purity determinations. We saw that solvation effects can decrease that onset temperature, and this is exactly what we see going on here very clearly. So with NETCH instruments, we have two primary DSC instruments that are designed for analysis of pharmaceutical instruments. We have the DSC 214 Nevio, and we have the DSC 204 F1 Nevio. We can see both of these are equipped with an automatic sample changer. One has a nice magazine for 20 samples. For high throughput labs, or labs that are operating both R&D and QC, or that have different groups, we have this much larger auto sampler for up to 192 samples that have these 96 well plate accessories with a sample loader that is barcode controlled, so that you can go through and load your materials in. If another researcher needs to come in and load other samples, they can load theirs, come back and reinsert your samples, and your analysis will continue on. These differ slightly in their temperature ranges, but primarily they differ in the number of samples that can be loaded and the automation that we're capable of. So in summary, we looked at polymorphs. We looked at polymorphs via differential scanning calorimetry, and we used the properties, the thermophysical properties of these polymorphs, their thermal stability, the kinetics of cooling, to look at different forms. We saw that polymorphs can have different forms that are more or less thermodynamically stable, some forms which are metastable, so that we can have materials that are in general less stable that are converting into more stable compounds, some that go through transitions from stable to metastable and back through to separate forms before melting. One of the reasons we want to use DSC as a characterization tool in combination with some of these other techniques is because the results are very fast. These are quite fast results. Instruments are very easy to operate. They're able to be automated. And as we saw in the very end, for some materials that might not be pure, that might have solvents attached to them, looking at DSC as well as TGA, or thermogravimetric analysis, we can get a better picture of what's going on within our materials. And one of the fantastic things here at NETCH is we also offer the combined DSC and TGA, so that both of these at all times can be carried out simultaneously. As you know, this is part 2 of a 4-part webinar series. We look forward to having you back with us next month, in October, so the 9th of October of this year. We're going to be looking at thermal stability and shelf life of pharmaceuticals, and we'll be doing that with infrared spectroscopy coupled to thermogravimetric analysis. So we'll be looking at kinetics of degradation, and we'll be doing some other studies using TGA coupled to FTIR. And in the final portion, we'll be looking at what many of you might want for your laboratories, which is fully automated routines. So basically, starting with loading a material into my sample crucible, how do I go from simple sample prep all the way to a finished report that just needs approval via 21 CFR Part 11 compliant software? So that's going to be the remainder of our series, and that concludes the webinar portion of this series. Now I'm going to go through and answer a few questions that we have. First off, again, thank you for being part of this series. Thank you for the questions that you have submitted, and I will go through and pull up those on the side here, and we'll get through to your questions. All right, so first question has to do with, this first question is from Steve in Illinois. Question has to do with the conventions, the DSC traces. Why am I seeing DSC, endotherms up versus down? Steve, maybe you missed the beginning of the webinar. This is just a convention. This is, in many cases in the US, endotherms are displayed in downwards, whereas European convention is endotherms are displayed upwards. So this is simply convention. I have another question, an anonymous question. This one was on the TGA curve. How come the TGA curve was run in an alumina crucible versus the aluminum crucible that was used for this hemihydrate compound? We could have run we could have run this in an aluminum crucible. That wouldn't have been a problem. This was just simply a choice of what we used in the laboratory. In most cases, for selection of crucibles, what we want to look at is to ensure that we have no interaction between the crucible or pan material with the pharmaceuticals or the excipients or whatever that we're analyzing. The first consideration is non-interaction. For a lot of pharmaceutical ingredients, this means that running in aluminum is ideal because aluminum pans are relatively inexpensive and disposable. They can be pierced, they can be sealed, and most of these transitions, actually I can say all of these transitions that we're looking at are occurring below the melting point of aluminum at about 600, a little over 600 degrees Celsius. So aluminum pans are ideal for almost all of your pharmaceutical applications needs. Lastly, if we're going to be doing purity studies or we want to ensure that we have highly clean crucibles, if your protocols or your methods dictate this, these crucibles can be solvent cleaned using acetone, ethanol, something that's 100% purity or ACS grade, pharma grade solvents, and then they can be baked. So we can ensure that we can heat these up and we can handle them appropriately to make sure that we don't have any oils, we don't have any residual solvents. This might be a little bit more tricky looking at ceramic crucibles. Ceramic crucibles also simply present a different heat transfer property. Aluminum crucibles, being metal, have extremely high heat transfer, and so we're going to have very, very high fidelity and a high response rate in our DSC using aluminum pans versus using, say, the ceramic crucibles that we saw in the TGA. On the TGA, since we're simply looking at mass loss and not heat transfer per se, we're not looking at heat flow, the simple mass loss of the water is perfectly fine. So really, this was a user consideration. And that's it. We actually only had 2 questions during today's webinar. Again, thank you. If you have other questions that you would like to submit that you maybe were a little too shy to submit directly through here, please feel free to add those in now. Any questions that you submit after the fact will be addressed by myself or by my colleagues over in Germany. Again, very last time, thank you so much for joining us. We look forward to having you next month for next month's webinar, and have a great rest of your week. Bye now.